This question is on the resolving power of a grating. So we have the question. When a gaseous element is raised to a very high temperature, the atoms emit radiation having discrete wavelengths. Two strong components in the atomic spectrum have wavelengths of 5890 angstrom and 5896 angstroms. So the question is, what resolving power must a grating have if these wavelengths are to be distinguished? Next part is to resolve these lines in the second order spectrum. How many slits of the grating must be illuminated So this is a question in which we have two closely spaced wavelengths, 5890 angstroms and 5896 angstroms, and we want to use a grating in order to resolve these wavelengths. So let us now solve the question. So for part A, now resolving power is defined as follows. We have resolving power R is equal to wavelength, average wavelength over the difference in the wavelength. So this is resolving power, where lambda is equal to lambda 1 plus lambda 2 over 2 average, and delta lambda is equal to the difference in the wavelengths. So in our case, lambda is 5890 plus 5896 by 2 angstroms. This is 5893 angstroms, and delta lambda is 5890 minus 5896 angstroms, which is 6 angstroms. So resolving power in our case is lambda over delta lambda, which is 5893 over 6. So plugging this in the calculator, we get approximately 982.167. So this is the resolving power. So the grating that we have must have a resolving power of at least this much in order to be able to resolve these closely spaced wavelengths of 5890 and 5896 angstroms. So this is the required resolving power. Let us look at the second part. Now resolving power for a grating in the context of a grating is also defined as follows. This is another definition. Here n is the small n is the order of spectrum and capital N is number of slits or number of lines illuminated in the grating. So this is another definition of resolving power. In our case, we want to resolve it in the second order spectrum, so n is equal to 2 for us, and we are given resolving power from part A as roughly 982. So we have, for our case, R is equal to 2 times n, and R we have from the above part, which again when we put in the calculator we get so number of slits n, number of slits to be illuminated, is roughly at least 491. So at least these many slits we need to illuminate in order to resolve the given wavelengths that we have. So this solves the question. The takeaway from this question was the formula for resolving power. So we had this formula, general formula for resolving power, and another formula specific to the grating, same for the same quantity resolving power. So we have two expressions for resolving power which can be used to solve problems like these.